Hi everyone, this is Team 8 of Electronic System Design 2 class. Welcome to our presentation from Milestone 2. Today we're joined by my teammates and myself, my teammates Matthew, Jason, and Lewis. So we are going to be talking about Rookman No Hands, which is a smart chess board that basically moves by itself. So a project is a smart chess board where all the pieces move by themselves. So if you're familiar with boards, chess boards like Phantom or Square Off, ours is a very similar gaming mechanism to that. So this basically enables the user to have a very unique gaming experience. So the project as mentioned earlier is you can play a game of chess locally or with virtual opponents or opponents who live far away. So all the pieces have magnets on them and are using an unseen head-style gantry system along with an electromagnet to move the pieces without any user involvement. So we're manufacturing a lot of pieces ourselves, and we aim to make a good and robust chessboard.
Since the last presentation, we've been working on getting our Hall effect sensors up and running. As you can see in the below picture here, we have gotten the onboard LED to light up when in proximity with one of our sensors. With a little bit of distance measurement, we've been able to determine that with a 2-inch sized chess square, we should be able to avoid any potential interference from pieces that are close by. We will only be detecting the piece that is directly over our sensor. In addition to this, we have checked out our 8-bit multiplexer. With this, we've been doing a small test where we cycle through lighting up a row of 3 LEDs. And we have indeed been able to get those to light up, which is nice. And in the above picture, you can see that we have built our 3x3 prototype test grid. And so with this, it's just going to be a 3x3 small scale version of our chessboard with all of the connections made as described in our last presentation. And this should be with the multiplexer library that we are using. It should be very easy to expand this to the 8x8 grid once that time does come.
So I'm going to discuss what we've achieved so far from a firmware perspective. So let's move on to motion control first. So motion control for basically the movement of the gantry. So we're going to be using G codes for the motion control for the gantry. So what G code is it's basically a programming language used in computer aided manufacturing to control the movements and operations of CNC machines. So it basically consists of a set of commands that specify tool paths and maybe like machine specific instructions for like manufacturing processes. So by generating the G code commands based on target positions, we can move the gantry along the X, Y, and Z axis accurately. So the ESP32 here will just interpret and execute these commands. So it will control the motors and ensure the movement of the gantry. So moving on to piece detection. So uh, basically the piece detection code is for detecting the position of the chess piece on the board. So the Hall effect sensors and the magnets enable us to track the position and the state of each square. So this code basically allows the ESP32 to read the Hall sensors and provide feedback on which sensors have detected chess pieces, enabling the chessboard to determine the precise position of each piece. So by processing the sensor data, the ESP32 can tell the position of the chess pieces. So from a server perspective, our chessboard is basically designed to connect with other services, other devices, and smartphones or far-off players, virtual opponents, etc. So we have a server that facilitates connection so far. So we're able to send and receive responses from the server, so which is what we need. And currently we're working on the game logic. So this includes algorithms for valid moves, the rules for check and checkmate, and also when the piece is like taken off or
I will now be reviewing the design progress on the gantry system. So as of the last presentation, the full CAD model of the gantry has now been completed, and we are currently in the process of manufacturing each of the individual components, which Jason will talk about later in a couple of slides. The design of the gantry system has been kept the same. It's an H-style gantry or an XY4 system. And an update on the manufacturing of the shafts. So originally we had planned to manufacture the shafts ourselves. But we realized that soon the tolerances that we needed for these bearings to not get stuck when they roll along the shafts are extremely tight, and we would actually need to place an order for them instead. So now I will sort of show you a video demonstration of the CAD mock-up for the H-style gantry system. So in this video, we can see the initial CAD mock-up. We have an H-style gantry system, which we can sort of tell by the H-style shape of the gantry. The movement of the gantry will have two of the linear blocks will be actuated by motors, so they will be able to go up and down. And we will wait for video to show the animation of the block moving up and down. And as you can see, there is a central piece in the middle of our H, which essentially is a payload for the electromagnet that will be carrying the electromagnet around the board, which will then pick up the pieces of the chess pieces and move them around to their desired position. And all this is done using two-stepper motors, which we will be controlling using G-code. And now we'll review the design progress for our chess piece design. So again, the CAD has been completed, and we are planning to 3D print these very soon. We will begin with the initial testing of the chess pieces by printing just a select few, so maybe a couple of pawns to see the fit of the magnet. And then afterwards, we need to find a way to test the material for which the chess pieces will be contacting the board so that they will slide around with not too much resistance when they are being picked up by the electromagnet.
So I'm going to talk a little bit about the design progress for the manufacturing design. So gantry design is completed. The next step is to turn it into physical parts. So we're working on the manufacturing plan, making sure that everything's set. We have all the materials required. Everything is in stock, so we're good to go. Unfortunately, I got sick, so got delayed a little bit in terms of timing, so that'll start next week. The main work that we've done is getting the bearing prototype completed. I have one right here, actually. You can see in the little screen. That's my bearing prototype. It's pretty smooth. The tolerancing is required on the diameter stack up. There's a little bit of wiggle in it. You can see that. The wiggle needs to be figured out a little bit. One thing that we did determine that is needed is we need some ground shaft. The length is just far too long to machine to tolerance. So with a smoother precision ground shaft and a little bit of careful machining operations with the bearings themselves, we should be able to achieve a pretty good tolerance. The rest of the gantry is fairly simple end blocks, and the only thing that was required is to figure out where the crucial dimensions are to ensure that the gantry remains square and flat, so it doesn't potato chip and create any issues with the magnet interfacing with the piece. All right, Dominic, I'm going to skip ahead. So another interview that we did, Bob Taglia is a master tool maker in the machine shop. I've known him for a number of years, and he's been helping me a lot with the design and manufacturing of these bearings, making sure that we can get them a little better. When he held this in his hand, he said it's a little crunchy, which I agree with. Part of that is kind of a rough finish on a lot of the parts. But once we get, again, that ground shaft in, it should help quite a bit. Couple pieces of feedback he had. One problem that I was having was on the diameter here, right? It's a steel casing with a plastic bearing race that holds the ball bearings in place. When you press it into the steel casing, the diameter constricts. So pressing it into place and then using a precision chucking reamer to get the diameter exactly where we want it to be is going to be very beneficial to ensure that it doesn't constrict onto the shaft. I had that happen to me once during the prototyping phase. So that's a very, very useful piece of advice. And the other thing is I have a design where there's two races, one here and one here on opposite sides of the bearing. Constricting it in 4 dimensions is going to help a lot. So just a little design change should help quite a bit. And hopefully we can get it a little less noisy and a little bit smooth and a little bit less jiggly on the shaft. I'm going to continue to work with him. He thinks we're in a good spot with this. Just need to tease out a few things, and we're not sending it to space, so should be fine.
So this is the Gantt chart which I had shown in the previous presentation, and from ever since the last presentation, we have made a bit of progress. So we made a small scale version of our Hall effect sensor grid, and we have fully designed the head style gantry and all the chess pieces in CAD, and we're going to start manufacturing. From manufacturing point of view, we have completed the prototype for the bearings. So also coming to the software perspective, we have completed some of the firmware. Like we have completed piece detection, and we're also working currently on using the G codes for the movement of the gantry. Suppose this, we will be working on the game logic.
One of the things that we've done the most in our time prototyping this project has been figuring out how to use third-party libraries that we obtain from the internet. One of these specifically, at least in my case, has been the multiplexer library that I mentioned previously. What this does is it greatly streamlines our implementation of any arbitrarily sized multiplexer just by using a single class that the library provides. It contains multiple methods for writing data on the input channel to any of the output channels and selecting which one of those you want to output it on. And this has just been a very valuable exercise in learning to decipher what someone else is trying to do with their code and use it to your own ends.
Our first question is regarding the feedback design of the chessboard. So we are currently thinking of different ways that we would want users to sort of interact with our chessboard. And we would like to sort of ask you the question of what are some designs for feedback that you might want to see the chessboard incorporate. So how would you like to communicate with the chessboard, maybe to get it to start a game or respond to certain movements that you would make, or have some sort of feedback system, or have the chessboard communicate something back to you. We just sort of like to hear any of the ideas that you might want to see rated there.
Now that we've figured out the major parts of our design, we have a little bit of time to brainstorm just for extra stuff that we could add on top. So we ask you, people who are familiar with chess, what features do you think you would find helpful and fun on an automated chessboard?
Thank you for watching our presentation, and we look forward to your feedback.